Okay, these notes should be very short. The first thing that you need to do is go ahead and correct the word at the top. The terms in these lists are terms of a sequence, but because we are summing them up, it is an infinite series that we are actually calculating. And the first thing to pay attention to is that it says right here that an infinite series converges if the ratio, and we need to stop right there, because as soon as you see the word ratio, that means that it's got to be geometric. It can't be arithmetic. So if you have a series that's arithmetic, or if you have a list of terms that generate a sequence that's arithmetic, there is no way to sum up the infinite list. Okay, and you'll see examples of why that's true here. But it's got to be geometric, and its common ratio has to be in between -1 and +1, meaning that its ratio has to be a number like -1/2, or its ratio could be +2/3. So you are multiplying repeatedly by numbers that are going to decrease the size of your terms. So if we looked at this first list right here, okay, and it's what we call a partial sum, which we did yesterday on our series notes, because right now it looks like we're adding the first three terms, but then you notice here at the end it's got the ellipsis, the ... which means you're supposed to try to total up the entire list. Well, if you look at the terms in that list, you go from 3 to 9 to 27. That means that you're multiplying by 3 between every two successive terms. So those numbers in the list are going to keep growing, and so what that means is that you can't total up the entire list. The list would total up to infinity, because the numbers in the list are going to keep growing all the way to infinity. So this is what we call a divergent series, because the terms in the list, so the terms in the list approach infinity as n approaches infinity. Now I know we haven't looked at limit notation in quite a while, but remember how to read this. This is saying that as n goes to infinity, so as you go to the 100th term, then the 1000th term, so forth and so on, the term values are also going to approach infinity. So this is divergent. We can't total up the whole thing. Whereas if we look at the second list, we look at the numbers going in successive order, and they are decreasing in size. We are multiplying by 1/4 over and over and over again. And what that means is that as n approaches infinity, so as we work our way towards the 100th term and the 1000th term and the 10,000th term, the numbers in the list are getting smaller and smaller and smaller to the point where they are approaching 0. At some point, the numbers in the list are going to get so small that they stop changing our total. So what happens is if you take the partial sum formula for a geometric series from yesterday, which was this, and if you have a series whose common ratio is a small number, like 1/4, like the one we just looked at, then what's going to happen is that when I start raising that 1/4 to some very large powers, what's going to happen is that this part right here is going to basically become 0. 1/4 to the power of even, 3 is 1/64. 1/4 to the power of 4 is 1/256. And it just gets so small that it becomes 0. And that makes this whole part of the formula simply become an invisible 1. It's 1 minus 0. So the entire messy formula from yesterday simplifies down to become this. If you look at a partial series, and if you look at the list or the terms that generate that series, if you have a geometric list of numbers and the common ratio is a fraction that's going to decrease the size of your terms, so it's a common ratio in between -1 and 1, then you can add up the whole list. Okay, now we're going to do an example of each one. Okay, so it seems silly to say this, but we did ask you to find the first partial sum for each of these lists. So the sum of the first term. So in this case, the first partial sum is 8. Okay, the second partial sum, or the sum of the first two terms, would be 12. The sum of the first three terms would be 14. The sum of the first four terms would be 15. So you see how the total is increasing, but it's increasing at a decelerating rate. First it increased by 4, then it only increased by 2, then it only increased by 1. We could even take it farther if we wanted to. If we wanted to do the fifth partial sum, then we would need to figure out what the next number in the list would be. And so hopefully you can look at that list and realize that your common ratio is 1/2. The numbers are being chopped in half each time. So the next number would be 1/2, which would make the 15th partial sum 15.5. And you could just keep on going. But the point is that now you don't have to. If I said, what is the sum? That's it. I didn't even give you a subscript. I don't want a partial sum. I want the sum of the whole list. We can now use this new formula that says take term 1. I'm going to go ahead and rewrite the formula just because it's good practice. So term 1 was 8 over 1 minus your common ratio. And the common ratio for this series was 1/2. So we would have 8 over 1 minus 1/2 is 1/2. And dividing by 1/2 is the same thing as multiplying by 2. And so we would have a sum of 16. So the sum of that infinite convergent series is 16. And it's called convergent, technically speaking, for two reasons. Because the numbers in the list approach 0, so the numbers in the list converge to 0, and the total of the list, or the sum of the series, converges to 16. Okay, now what's going to happen if you have a divergent, so this was convergent, let's write this, convergent. When you have a divergent series, then what happens instead is this. Let me change colors really quick. Let me erase to make some room down here. Okay, so once again, first partial sum would just be the first term. It's not even really a sum. Okay, the second partial sum, the sum of the first two terms, would be 4. The sum of the first three terms would be 13. The sum of the first four terms kind of ran out of room, would be 40. Okay, so if you look at your totals, you go from 1 to 4, so it increased by 3, then it increased by 9, then it increased by 27. So not only is the total increasing, it's increasing at an accelerating rate, not a decelerating rate. So it's speeding up. It's getting bigger and bigger and bigger, faster and faster and faster. And so the infinite sum does not exist. You can't total up the whole list because it is divergent. So it's geometric, but it's diverging. The numbers are not approaching something specific. So that's it. That's all there is to infinite series. We'll have one other day of flipped notes, which will give us quite a bit of work time in class this week, hopefully. Come see me for tutoring if you have any questions.